So welcome today on the presentation about Reactive Extensions to Reactive Streams. And my name is Bartosz Sypytkowski. Who am I? I am one of the Akka.NET project contributors for like 4 years right now. And for those of you who don't know what Akka.NET is, it's essentially a port from the Scala version of Akka framework. It's a framework for distributed actor model programming. And what we will talk about today is, let's first start from warning, because some of the ideas here might seem to be a little bit controversial. And what I mean here is that we will try to challenge some of the ideas that may or may not be considered as absolute truths in .NET framework as well. And what we will talk about specifically is streaming paradigm for building data flow based applications. So we'll talk first about the theoretical background for that. We'll see different approaches to it and how did they evolve essentially to reactive streams. And later on, we'll take a look about some more practical aspects on that built on top of Akka.NET Streams, which is a plugin library for Akka.NET. And what perspective I would like you to pick here is that you would need to think about SPIs for the first part and APIs for the second part, and what they are and how they differ. We'll talk about in a second. So, APIs versus SPIs. What the APIs is, it's an acronym for Application Programming Interface, and what it essentially is, it's a contract between library creators and library users, so us as programmers, for using that library, basically. And this comes with some of the assumptions, some of the design decisions. So, for example, first part, this API is used on a daily basis. It's used often. Another is usually associated with some concrete solution for the problem, because if we want to use a library, it should solve some kind of a problem. Another one is that for every problem, every solution must have some trade-offs involved. There are no silver bullets here. We usually have to make some decisions in order to achieve the problem, and therefore there is a reason why there are different libraries solving the same, having the same area essentially, because they are picking different trade-offs. That depends on actual use cases. And what comes with that is that they might be more like Microsoft libraries or less opinionated. And I've added a question mark here because this is not always true, and this is not necessarily an issue, because usually we might like opinionated libraries for the fact that they have picking up the burden of making decisions for us, as long as those decisions are in line with what we are actually doing. Once those decisions are no longer applicable in our case, these opinionated frameworks can be problematic for us. But what is most painful about designing libraries to be API-based? Usually when we create a project, we use more than one library, more than one framework in our system. And often we need some kind, to connect them. So what do? We type NuGet, and later on we are checking for adapters between the two. And the problem here is that now we are in the vast area of potential adapters, because we basically have each-to-each mapping between one library and another, in order to be to make them compatible with each other. Also, what comes with that is the fact that APIs are changing. So, our adapters and our libraries can get, essentially, unused over time, and we need to update them and fix the dependency conflicts and so on and so on. And this is where SPIs come to play. So SPI means Service Provider Interface, and what they are designed to do is essentially to provide a contract between different sets of libraries that they can agree upon in order to operate with each other. And this comes with a different design decisions in mind. First of all, they are not used so often because they are used mostly by the library creators, and mostly they are designed for another libraries being consumed. What it also means that they usually don't change that much as a normal APIs. Another thing is that they focus on providing abstraction. So they don't need to provide a specific solution for the problem, or rather a set of interfaces that we would like to use as our contract. Another thing is that they have minimum or no dependencies, because essentially what it's important for us as library users is that once we have dependency on some library, we also need to care about the transitive dependencies here. And for this, we probably don't want to have to download 100 megabytes of dependencies just to implement a single interface. This is not what they are meant to do. They are single purpose, and we can see that those kind of libraries are already existing in .NET space. For example, all of the Microsoft.extensions, something .abstraction libraries are basically SPIs for our current state of .NET ecosystem. They are solving particular problems like logging, dependency injection, configuration, and so on and so on. And ideally, they should be elastic and agnostic for the programming paradigm, because we don't know who will be working with them, but we want to be elastic enough so that they could be implemented by either object-oriented programmers or functional programmers, depending on what we would like to use. And the contract needs to be well-defined, and ideally, it should have some kind of specification, because not everything that can be explained using only the type system. Some of the constraints related to using those interfaces are cannot be expressed using type system. So today we will talk about those three different libraries or approaches as potential ways to be used as an SPI. So we'll start from reactive extensions, then async enumerables, which I know that this is not a library because there are different sets of libraries that essentially implement the same interface in .NET space. And the last one, reactive streams, as essentially the final, I would say, proposal on how the streaming could look like from the SPI perspective. So keep that in mind. So starting from reactive extensions, it's essentially a set of interfaces, to be honest, that allow us to create push-based streaming applications. Push-based means that the pace of the processing is dictated by the producer of the message. So here is the basic set of interfaces that are necessary to establish this contract. And what you can see here, for example, iDisposable. It's actually also a part of the contract, but it's implicit because it's part of the .NET standard library. But what we can also see here in the subscribe method is that during subscription, we are returning this iDisposable object, which means that essentially this method is expected to be executed synchronously, for example, which is quite limiting in some situations, because we need to await for the subscription, which could otherwise happen asynchronously, for example. But what is more important here is the problem that this library produces. For example, what will happen if we have one producer that is able to process 100 messages per second and consumer that it's a lot slower? Now we are landing in the situation when the consumer is no longer able to stop the producer from producing its messages simply because there is no way in this SPI, in this interface, to inform about that. So what we lack here is a lack of back pressure. And usually it's not a problem in client-based applications. That's why, for example, I think that's why reactive extensions are so popular on the client side, because when building client applications, the pace of the work done by the producer is strictly related to the number of actions that a single person can essentially trigger. But for the server-side applications, when we can have thousands, hundreds of thousands of clients being producers of messages, this could quickly turn to overflow our servers. So there is a well-known alternative approach, which is called async enumerable. And it's a different kind of string model. It's pool-based string model, when the pace is dictated by the consumer of the message rather than the producer. And this is a variation, I would say, of the iterator pattern, with this distinction that our moveNext method doesn't have to return immediately. Instead, it can return an asynchronous continuation that can be completed by the producer whenever they have a new message to actually push to the consumer. So this interface is really, really clean. To be honest, I really love it. It's essentially a single method, if we would look at it from the right perspective. And it's very self-explanatory, and it's so great that it's, and I think universal, that it's actually used in the, will be used as a first-class citizen in C# soon. However, let's start, So yeah, how does it look like? So first, when we are talking about publish-subscriber model, because all of those are essentially representations of publish-subscriber model. So the subscriber first needs to request the next message from the publisher, and then the publisher can, complete that request. And this allows us to, produce the back pressure. However, let's do some nitpicking here, because while this set of interfaces allows us to go for the great lengths, it has also some limitations. And here I will focus on two of them. One of them is low overhead, high performance scenarios. So for example, if we look at this piece of code, we can simply assume how many async objects we'll create. It would be 3 per invocation times million. So around 3 million of asynchronous computations will be created just to, increment the array weight 3. And you could say, this is stupid, because nobody would write code like that. However, it turns out that you can write a very similar code that has very similar characteristic. It just, it's a little bit more confusing. So you won't see this pattern here, but it will exist still in our application. And why does this number of allocation matters? Because let's talk about tasks. I've picked tasks here, not F# asyncs, because the tasks are more well-known area for me. But from what I know, the characteristic of async in F# is worse than tasks, so it matters even more. So first thing is that tasks are allocated on managed heap. Essentially, from what I've heard, they have around 88 bytes of memory. And when you are actually scheduling them on the thread pool, this number goes up to like 300. And you could say, well, it's not that wrong because we can simply garbage collect them, but there is another case. Tasks are disposable objects. And I know that probably none of you have ever disposed your tasks. I know I didn't. And essentially, why? Because we don't care about that, because tasks have custom finalizers that do that cleaning for us. However, where's the problem? From what I've read, when garbage collector is trying to, for example, collect the object with custom finalizer, it's first promoting it to Gen 1 before actually, garbage collecting it, which means that this garbage is no longer that free as we think about it. So one thing is that they are they are not that heavy in most of the scenarios, but in some of them are. And the last thing is that tasks and asyncs are solid implementations. So if you want to create your own tasks, or you have idea, for example, how to bring a better implementation of task API, or some competitive library to TPL, you are stuck because right now the whole API is using tasks. So you still have to move to this baseline, even though maybe your implementation is better. Eric Meyer was proposing a async sequence as async return being a state machine with essentially 3 different states: pending, completed, or failed. And this would work great in case if this would be actually this kind of an abstraction that we can specialize over. But we can't, not in .NET, not in the current state of the art. And another kind of problem is when we have a slow continuation. So for example, any kind of I/O. Any kind of I/O done over the network or over the disk space. Because imagine we are now picking elements one by one from over the network. Let's say that processing that item will take 1 microsecond. Picking it up from the network takes 5 milliseconds. You can see what the overhead we have here. And there is a simple solution for that. It's called batching. So instead of using picking elements one by one, we can pick them in batches. However, there is another problem with that. So let's say we have requested for the next batch of elements. We are picking 10 of them. We are requesting the next one sometime later. But in that time, the spike has happened on the producer side, somewhere in the upstream. So in the result, we received 10 millions of them. We don't even know if we have enough memory to actually work with them this way. And essentially, we come back to the problem of unsafe operations on the server side. So, of course, this is easy to solve. We can set maximum bound for the batch to happen, but there is a problem. This is something that is very specific to our implementation, and our consumers do not know anything about it. So it would be nice if we would be able, for the consumers and producers of messages, to be able to tell not only that they are requesting and they are able to process the next message, but also how many of them can they get before getting overwhelmed. So let's say we have a sideline when a consumer can send information to the producer, like, give me 3 more messages because I know I can batch 3 of them in my memory before I will run out of it. So now it's up to the producer to remember how many of the messages has it sent to the consumer. So let's say that producer has only 2 of them. He's sending the 2. He's reducing the counter for that subscriber, so he knows that he can push 1 more message before, waiting for the next request. In the meantime, consumer asked for 2 more because let's say we have a fast consumer. And the 3 different, the next 3 messages have arrived in the meantime on the producer side, so it's pushing them back to the consumer in 1 batch because it knows how many of those can push. And Yeah, welcome in the reactive streams, because this is basically the idea behind the reactive streams. It's known as a dynamic push-pull-based streaming. Probably there is some asynchronous or other kind of different, hyped word around there. And I know that a lot of people are calling this, that this is actually stupid, because reactive and interactive, how the async enumerables are called, are well-defined concepts, and this is just a buzzword. And yeah, you are right. Basically, what we have here is a pull-based streaming, but with support for implicit batching. And what do we have here? I will come to the push-based part later on. So this is the entire contract here. So we don't have observables and observers. We have just publishers and subscribers. We have also the processor, which I think that in Reactive Extensions for .NET is called a subject. So it can be subscriber on one side and publisher on the other side. What we also have here is subscription, which replaced the disposable object as it can cancel the stream and cancel the subscription, but it also can be used to send requests to our producers in the upstream. And what is important here, as you can see, all of those methods are not returning any kind of value. And why is it important? Because this way, it doesn't matter if they are working synchronously or asynchronously. We can start asynchronous job inside of them and use other methods inside those interfaces to tell basically the other side when some specific action has happened. And the importance of the request method is that it allows us to send the demand, the ability to consume from the consumer to the producer. So for example, demand is just a number. And what can we do with it? Let's say that D has sent a request for the next 5 elements to C. However, C is a bit slower, so it sent 3 elements to B. And B, it doesn't really matter what the performance it has, because it decided to keep up to the slowest consumer in its downstream and send 3 messages to A. And this way, we are able to adjust our processing capabilities to the slowest consumer, so we don't overwhelm our application here. Because demand is number, it can be also split and aggregated depending on our needs. And it can be increased or decreased depending on if we are dynamically adding or removing subscribers. And this is also a great way of dealing with splitting the demand across the different stages. And it turns out that this interface is easy enough that it can be used to represent the same processing logic that all of the previous models have proposed. So for example, here is how to create an observable in terms of reactive stream interfaces. The magic happens in the request long max value method. And what it does mean, it's essentially a part of specifications, which means I can, as a consumer, I'm notifying my producer that I don't care how many messages will it send to me, because I'm sure that I can process every single one of them. So I'm no longer, as a producer, I'm no longer trying to count them. I can just, put them on the full trust to the consumer. Other side, we can also create async enumerables around reactive streams, because here we basically can represent move async and completing this async as basically a request one and on next combination. So essentially, asynchronous enumerable is just like reactive stream that always requests a single element on every single call. And now we can ask, can we do more actually? And it turns out we can. What about representing tasks themselves as reactive streams? Because task is essentially a specialized version of reactive stream, of iterator pattern. It's basically a stream that has only a single element. So we can represent it that way. And I'm not telling that you have to, just to be clear. However, to be honest, it already has been done. In .NET, in Project Reactor, if I'm right, there is something called Mono, which is a single element stream optimized for this kind of computation. And on Java, essentially on Java, the whole Reactive Streams is now part of the standard library. And they are used for most of the asynchronous computations there, and most of the streaming libraries, because they have many of them, are implementing reactive streams as, you know, a common denominator to talk with each other, as it's meant to. So if you have some ideas, I would encourage you to use it. There is also a thing called AirSocket, which essentially takes this notion of demand, also things like multiplexing and request response patterns and so on, and put it over the network on top of other protocols like TCP, WebSockets, or Aaron, if you ever heard about this. It was called a Reactive socket in the first place. However, they decided to change it to the AirSocket because Reactive became so polluted word that it's lost its original meaning, essentially. So it's now called AirSocket. And if you will ever want to create your own streaming library, or just use reactive streams, you can check their compatibility by using something in .NET. It's called Reactive Streams TCK for the test compatibility kit. And it's essentially a NuGet with a set of libraries you can inherit from and inject your own implementation of your publisher or subscriber in order to test if it's compatible with Reactive Streams specification. Because this specification has, like, I think, hundreds of points to fulfill, like things that you should not ever push messages when you have not demanded for them on the other side, and so on and so on. But if you want, you don't need to write this specification compatibility test for yourself. You can just pull this library and voila, it's ready. And this was the part when we talked about service provider interface. Here, we take another part, which is more practical examples, where we will talk about Akka.NET streams, which are implementation of that pattern of the reactive streams over the actor model. And if you are not familiar with actor model, it's really nothing bad, because we will not talk about actors almost at all. So, as specific implementations, there were some design decisions in mind. I just figured out them, so it's not written, and they are not always true because those constraints can be relaxed. One thing, I would say that this is the server-side first library, mostly because some of the operators that are, for example, represented in reactive extensions are not here, like distinct, because distinct would not work well on the server side because you will basically need to batch every single element that you ever received in your stream. And this doesn't sound well in a situation when you can have billions of those processed over the day, for example. So I would figure that this is the case. Another thing, that this is also created for long-running streams. I mean, like streams running at least for seconds. This is also not completely true, because there is a way to tune it from code and from configuration to actually make it applicable also on the short-living streams. It's built with predictability in mind. So, for example, when you are creating a server-side application, and let's say your client has sent you a file that contains some lines, and you want to read those lines, and read this file line by line. Have you ever checked how big buffer have you allocated for the line that you are reading at the moment? What if you have thousands of clients that send you, for example, gigabyte-sized file when there is only a single line, and you need to buffer it before reading it? Buffer it entire message in the memory. You could also overflow your network. So here, for example, a lot of the settings we are using require you to specify that value explicitly before you will actually use it. So it's a little reminder for you that those things exist and those things matters. And it's also a static, because here we are representing publishers and subscribers as stages with connections, and there is always a limited number of connections. So there is always a limited number of subscribers that can be subscribed to a single publisher, and so on and so on. And this number needs to be known ahead of time when you are creating your streaming workflow. And this is also not entirely true, because there is a thing called hubs, which are specialized version of stages that essentially they give you a point in which you can dynamically add or remove subscribers, but those are specific points in your entire workflow. You cannot just add or remove subscribers ad hoc during the runtime execution, and we will come why in a second. So just like we have this publisher processor subscriber idea for reactive streams, in Akka streams they are called source, flow, and sync, with this distinction that, as I've said, they have a connection. So source can, for example, have multiple outputs. It's only producing messages. Flow essentially is message transformer. It can have more than one input and more than one output of it. And sync is basically a final message consumer, so it only can consume messages from multiple inputs potentially. Okay, so now let's come to demo. I hope I haven't bored you to death. Okay. So here I'm using Async, which is F# wrapper library over Akka. So this code will be in F#. Can you see it? I hope you can. Okay, so the quick explanation. For Akka to happen, we first need to create an actor system, which is system.create in Async. And this establishes a container for your actors, because whenever, even if you are working with Akka streams, they are materialized on the actors underneath. Then we are creating materializer. I will talk about it in a minute. And then we are using Async DSL to define our stream, essentially. And here it's a very simple stream. So we are taking a finite number of elements, map it 3 times, incrementing with each time, then map it to the string, and then printing in run for each. And the last thing is that we are calling async run synchronously, because essentially the whole API is designed to run over situation when we have non-finite number of elements. So we don't know when this source on the stream will complete, and we don't want to block our current thread for that to happen. So there are a lot of dependencies inside, but yeah, it works, hopefully. So as you can see, we just get numbers from 1 to 10, incremented them 3 times by 1. It's not the same as incrementing them by 3. And then we printed them. So this is something like hello world in Akka. And we will use it for future talk when we go to more advanced concepts. You don't need those. Okay. So when you have a glimpse of the code, we'll take more advanced concepts in a minute. We should talk about a little bit how this stream materialization process works, because I'm talking about it from quite a while, and you haven't probably heard of it before. So essentially, And the whole stream execution can be modeled as a combination of two things. One is the shape. Shape is what we are creating using this DSL, this Linku-like DSL, because in C# it would look like Linku essentially. And what is important is that this shape doesn't actually execute anything. It's only a blueprint, let's say mental model on how our stream should be executed once it will be executing. And this is why I was talking that this configuration of your stream needs to be static. Because in order to execute it, we want to have a complete picture of how our stream will look like. And when I'm talking stream, I actually mean graphs. Because Akka streams is all about graphs, but streams are, flows are essentially a very simplified version of graphs. And once we have all inputs and outputs connected, we are ready for the materialization process to occur. And for that, we need a materializer, which is essentially a component that is taking this blueprint and executing it on the actual machine. And what is quite nice here is that this pattern is well known in functional programming. It's known as free monad. Yay! There is a monad word in this talk. Depending on if you are a functional or object-oriented person, you might be either excited or terrified. So don't worry, because there is a very similar pattern in Gang of 4 books, and it's called interpreter pattern. And if this still doesn't give you a relief, you probably, if you are a C# developer, you probably have used iQueryable for quite a while. And this is essentially a very similar pattern to that. However, in iQueryable, your queryable is essentially a monad, and it has some implicit embedded field containing the interpreter, which is known there as a query provider. Here, we are calling it materializer, and we are putting them out of the shape itself, outside, and we need to provide them explicitly in order to avoid accidental materialization, which can happen and is happening actually in day-to-day code when you are executing queryables. Because it's nothing easier that query the entire table and call to list before making a paging over that list, So we don't do that here, and it's not possible even to compile. Okay. So another thing why materialization is important is that we can provide a various way of interpreting our blueprint into real life. Essentially, for example, in JVM version of Akka, there are 3 materializers. The default one, the phasing materializer, which essentially is designed to work with short-living streams, and it's focused more on making materialization process itself faster, because it can take a while because of those optimizations. And you have a gear pump materializer, which essentially takes your blueprint and picks the points in which you can, for example, spread your graph, execution graph, on the entire cluster of machines. And all of them works over the same, basically in the same blueprint, but they are doing very different things here. And what else is important here is that given the entire shape basically at the materialization moment, the moment when we are materializing it, we can take a look at it and do some optimization. The simplest one are, for example, picking up identity operations. So operation that doesn't do anything. Essentially, it takes element from the input and puts it on the output. You can erase those. Another thing is related to async boundaries, and this is very specific for Akka so far, because we have different kind of stages. The simplest one, like where select, or in case of F# filter map, can be as well executed synchronously. And in the past, every single stage in Akka was executed on its own separate actor. But this was quite an expensive process, because even if communication between actors is fast, it's not enough fast it's not as fast, actually, as basically taking output from the one stage and putting it on the input on the another stage right away. So what we can do, we can take a look and pick the stages that could potentially be executed in asynchronous fashions, potentially on multiple threads. Map async, which takes an input and returns async of output, is one of them. Another one would be, for example, group by, because if we are spreading the operation on the some space of substreams, we could as well make it multi-threaded by default, by nature. And we put async boundaries on those places. So what we are left with are bunches of operations that can be executed synchronously. And what is coming then? It's fusing, sorry. So instead of executing every stage on its own, we can merge them together and execute them on the single actors. So this way, those operations are becoming way easier to execute, and they are way more lightweight, because essentially, right now the overhead is minimal. It's almost like you are running for loop in this case. So what can we do with it? Essentially, akka DSL provides around 140 or maybe close to 200 different stages right now for making different kinds of operations. And what is nice here is that we can reuse them in different contexts. One of the contexts is Async Stream IO, which is basically building a socket server, TCP or TCP socket server over the actors. And what it does for us is that it handles all of the dirty parts which are related with working with sockets if you want to work with them by yourself. So it's handling things like multi-threading, buffer pool management, and anything like that for you. It's quite similar to what Microsoft done lately with system I/O pipelines. And I think that we can demo it right here, because it's a little bit exciting for me. Okay, so let's go to the, where's the mouse? Oh. Okay, so close that one. And let's see how, for example, a TCP server looks like. We'll start from the bottom. Essentially, we are creating a TCP stream. We are binding it to a specific port and endpoint. And what we have in the result is the source that is producing a new connection event for every single client that is connecting to our server. And what we can do here is essentially running a for each, asynchronous for each, because in the connection itself, there is also a flow. So we have a flow of flows, essentially. Flow in the connection is representing the socket itself, because if you think about socket, it's essentially a flow which basically takes some inputs and sends it to another machine over the connection, over the TCP connection. And for every incoming message from the TCP connection, it is sending it as some byte chunk in the output. And this is what we have here, essentially. So graph run mat is essentially running a graph over some given materializer. This is this explicit phase. Why graph? Because, as I said, everything here is a graph. And what flow join is, it basically takes two flows and combines them. So we have a closed circuit here, complete graph, with no loose endpoints. And what we need here is essentially, what we are left with is essentially a handler. What is the handler? The simplest handler version is essentially that, flow empty or flow ID. And it would work as an echo server, because it takes an input and puts it on the output. But here, we want to make something more. What I want to do here is essentially take a line of input from user, add, log it, add some suffix, those 3 bank operators on the end of it, and put it back to the server. So it's echo with extra parts. And for this, we need a framing delimiter, because as you may know, the sockets and TCP in specific are not working over the messages. There is no notion of message in TCP. You have data frames. Those data frames can be the same length as your messages, but they can be shorter or longer. So what the framing delimiter is, and what it does, it's essentially a flow which picks byte strings from the input and buffers them as long as it is trying to find the delimiter. Here it's a new line symbol. So when it found that, it's splitting those byte strings and it's concatenating the parts buffered together as a new single byte string, and it's pushing it along the way. So let's execute it. And I will send some messages to it. I will use telnet here. And the port was 5000, if I'm correct. OK. Yay! I don't know if you can see it. I wrote hello NDC, and I've got hello NDC with 3 banks. And also, I've logged it here, and I've got information that the client has been accepted. I used the wrong endpoint, sorry, because with connection you have 2 of them actually. One is the remote endpoint, and one is the local one. And I think I've used the wrong one. Yeah, local address. I should use the remote address here. Sorry. And OK, so this was the example for the server side. The client side is also quite simple, because I think that this is actually quite simple, because once you will realize how to build things in terms of streams, you can apply this knowledge basically everywhere, because streams are composable and they are composing very well in very different scenarios. So the client is essentially a source that is sending a single message, hello NDC Oslo. What we are receiving, we are essentially printing on the client side. This map value would not happen in C# because this is related in the ways how we decided to use. There is a thing in akka that it's called not used type, and it's essentially the type that doesn't do anything. And in F# we are using units, so this is way to map one to another. What now? We are constructing a flow from it, because we can, given a sink and source, we can combine them and create the flow this way. And then on, we are creating outgoing connection. We are combining it with our flow, and we are running it. And I think that I've killed the server, so I will run it quite OK. Ooh, it should, yeah. And here is the client. I will run it. And yes, there is hello NDC Oslo. And also we got it here. So yeah, this one is working fine. So right now, come back to our presentation. Sorry for that. I think we won't need it anymore. OK. So I was referring to this notion of byte strings. And the case here is that what the byte string actually are. What they are is the abstraction we put on the managed buffer pools. Because essentially what we would like to work with is thinking about them as a single continuous space in the memory. However, this is not applicable in real life, because we would need to copy different chunks of strings if we want to combine them and so on. So byte string is essentially, from the outer point of view, it's a single continuous piece of memory that is immutable. And what we can do with it, we can slice it, we can combine them, and take another byte strings. However, underneath, it's actually represented as something like a read-only list of read-only spans, I would say. So we have lists pointing on some frames of memory, and when we are actually slicing and combining our streams, we are just moving those pointers along without actually copying any memory buffers this way. This way we can be quite fast and don't allocate too much because we are just moving the pointers all along the way. So the next thing is called BD flow. BD flow is essentially a flow that have 2 inputs and 2 outputs pointing in the reverse directions. And why it's so great? Because this is the way that we can combine something like web parts from SUAV, HTTP handlers from Giraffe. Because BD flow can be combined, for example, with another flow and create a flow in the result. 2 BD flows can be combined together to produce third BD flow. And what we can do with that? If we are able to represent TCP socket connection as a flow, we could use, for example, BD flow to represent TLS over that. Then we can use another component, which would be a BD flow, and apply, for example, HTTP layer over that. Then take some authorization layer over that. And we could combine those layers together in forms of BD flows. But this is not the only applicable solutions. For example, we could create a BD flow that is working as adaptation layer from our event source stream that is basically mapping events from the older versions to the newer versions that we are actually using. The applicable solutions are many, and this is basically the power of composability itself in the purest form I can think of. So I was talking about the graphs, and another applicable case is building the entire graph. That it's not, simple single flow solution, but it can also have, multiple consumers, multiple producers, and what is more important here, Akka.NET is one of the very few solutions that allow you to build and include cyclic graphs in your solution. So we can build a feedback loops here. And because we have not enough of time, I will present a very simple example of how GraphDSL works. Okay. So how does it look like? Here we are creating a graph. This is essentially this part of code. It's very specific for Acklink because you cannot build a custom interfaces, custom operators in C#. And what we are creating here is basically a graph which starts from a single source and has a single sink on the other end, and in between it basically is mapping the values and printing them, and then putting the same value to the feedback loop, back to before the flow actually executed. And this can be represented this way. So from source, we connect to merge flow, merge stage, which then connects to the flow, which then connects to broadcast. What are merge and broadcast? Merge is essentially a stage that is picking one input and 2 inputs, sorry, and combining them into one output. And broadcast on the other way around, so 1 input, 2 outputs. And here we are combining, for example, broadcast with merge. Preferred means that before we will take a look at any other, input from our merge, we always pick preferred as the first. And what we will create this way, we only send a single message from the source inside, and you will see what will happen. we basically have infinite loop, because we never pick this message from this feedback loop, and we always are putting it back again. So even though we send only a single event inside, we have, basically infinite circle here. And this is also why it's important to actually remember that this is a very risky case for you, and it should be tested thoroughly. But it's possible. It's possible to work this way. So, the next thing I wanted to present you is how to use the same semantics, the same string semantics for akka persistence query. And for those of you who don't know, akka persistence itself is a plugin that allows you to create persistent actors that are storing their state through sequence of state changes, so events. And what we have here is basically a native support for event sourcing. So every single state change over the actor is stored as an event in some kind of pluggable database. And what akka persistence query is, it allows us to read those events as streams of data. So another example. So here we are creating a simple actor. Oh, sorry. Okay. So here we are creating a simple actor. It can take one type of command and one type of event. Command is order item, which in turn will persist our item ordered event in the persistent storage. And item ordered is essentially an event that we want to replay from. Then we are creating a source, because I don't want to put those values, put those commands manually. So I'm creating a source in which I will trigger every single second this actor to store the new event inside. And then I'm creating a source from this event stream. And what is nice here is that this stream is essentially implication of the live query. And what I'm using it here as a persistent storage is a SQL Server. So wait a second. What do we have here is a stream that is reading events as they will come here back to us. We started from 44 simply because I haven't cleaned up the table in the database when I was storing those events before this demo. So yeah, we are sending those values back again, and we are reading them as they come up, as they are stored by our actor, essentially. So yeah, we can build live streams over the databases that don't support this out of the box. Another case, and we are close to the end. There is the one last thing I wanted to show you, which is stream refs. And this is something that doesn't exist yet in akka, as you can download it from NuGet. It's something that will be part of 1.4 release. And stream refs are essentially the same thing that actor refs are for normal actors. So they are handlers or references to the stream that can be serialized and deserialized over the network, materialized on the other side in different actor system, and they will still connect to basically old actor system and stream that lives there. They are safety typed, and they have back pressure mechanics baked in. So in order to present that, I will unfortunately need to turn to Visual Studio and C#. And what we are doing here, sorry. I hope you can see it. Here is our producer, where we have a simple actor that when we request it will return a source ref, so-called source ref, back to its original sender. And in the source ref, it will also make a tick every single second. And what we have on the other side, in the another actor system, is that we essentially ask for that actor to get a source ref from it, and we materialize it on the other end of the application, on the another process essentially. So let's run it. Does it work? Oh yeah, sorry, it works, but you can't see it. This is the producer, and this is the consumer. So yeah, we have two different processes when a stream is spanned over the network between different processes, different systems, and probably different machines. So yeah, this was the example. And the last thing, thank you, and I wanted to thank every single one of the contributors, because akka.net is a community-driven project, and without contributors, without your help, we couldn't make it. I also wanted to help every person who make a bug issue on the GitHub and help us to make this framework mature and actually usable on the production. So thank you very much.